Hello and welcome to this video today where we're going to have a look at exam questions, past exam questions, specifically on reflection and on spherical mirrors. So we've got 1, 2, 3, 4 questions we're going to have a look at today from past exam papers. The first question we're going to look at is a 2018 question 11. And this is actually a question where a multitude of different topics have come up, but there's 3 questions specifically on reflection and spherical mirrors. So we're going to look at those 3 questions today. So question 11, part D. The first thing we're asked to do is calculate the position of the image of a person standing 75 centimeters in front of the Levantian mirror. From the previous snippet, we can see that we are told that the focal length of that mirror is 16 meters. So therefore, we have everything we need in order to do this question. The first thing I always say to all my students is write down all the information you're given in the question. So first up, we're going to write that the focal length is 16 meters. Second thing, our image, our object, our person, is standing 75 centimeters in front of the mirror. Now, one unit, the focal length, is in meters, and our second unit, the person, is in centimeters. So we want to change that to meters. So that becomes 0.75 meters. And the last thing, V, our image. Where is our image going to form? That's our unknown. Second thing to do, guys, always write out your formula. You're going to pick up most likely 3 marks for writing out your formula, so that's a good habit to get into. And now we're just going to start subbing information in. We know U is 0.75, V is what we're looking for, and F is 16. At this point now, what we're going to do, some algebra. We're going to take 1 over 0.75 and take it to the other side of the equal sign. So we have our unknown on the left hand side of the equal sign, and we have all our known values on the right hand side of the equal sign. We should also note, when you take something across an equal sign, it changes sign. So that becomes minus 1 over 0.75. At this point now, guys, just grab the calculator. And we're getting minus 61 over 48. Now, at the minute, guys, we've got 1 over V, but what we're looking for is V by itself. So what we can do at this stage is just flip this fraction upside down, or flip that around. And if you do it on one side of the equal sign, you can also do it on the other side of the equal sign as well. So that becomes V over 1, V divided by 1 just stays as V, and now we've got minus 48 divided by 61. Into the calculator, 48 divided by 61 gives us 0.79 meters, which is, and there's a minus there, 79 centimeters. Now, it's important not to forget about that minus. What does that minus indicate? Well, that minus indicates that this is a virtual image and that the image is formed behind the mirror. So that minus indicates that this is a virtual image. It cannot be projected onto a screen. Okay. Now just bear with me 1 second. We'll go back up. So we've been asked to calculate the position of the image. We've done that. And where, with respect to the concave mirror, will an image of the moon be formed? Okay. So what we've got here, if we look back at the question, is we've got a telescope which was built in 1845, and it was the biggest telescope of its time. Now, obviously it was used for looking out into space, and in this case we're talking about looking out into a moon. Now what we should note is, or what we should be aware of is, when you've got a distant object like a moon, and we've got our telescope right back here, or we've got our concave mirror within our telescope, let's just draw our principal axis. Okay, and there's our focal length f. Any light coming from a distant object, okay, we should be aware of this. Any light coming from a distant object, in this case the moon, comes in parallel to the principal axis because it is traveling such a long distance. So what we should remember from our rules is, light that comes in through our principal axis, or comes in parallel to our principal axis, should I say, travels out through the focal point. Okay, so the answer to this question is, where will an image of the moon form? The image of the moon will form at the focal point. Just to recap that one more time, light from a distant object, in this case the moon, it's obviously quite a distance away, that light will travel in parallel to our principal axis. If you've got a light ray traveling in through the principal axis, it will, as a result, reflect back through the focal point. So our light rays intersect at the focus. And that is part E. Justify your answer. Okay, so it'll form at the focal point. That's what we've said. Justify your answer. We need to now say light rays traveling from a distant object travel parallel to the principal axis. Therefore, reflect through the focal point. Okay, and that is our answer to part E. Now, part F. So, we've got a concave mirror, can also be used as a microscope to magnify images. Draw a ray diagram to show the formation of an upright magnified image in a concave mirror. Okay, so this is our diagram, guys. Need to be familiar with drawing these. First things first, I'm just going to draw my principal axis. There we go. Going to draw my concave mirror. Dashed line at the back representing that that's the back of our concave mirror, and I'm going to put my focal point there. Now, what we should recall from our notes is that if you want an object to form upright with a concave mirror, that object cannot be outside the focal length. That does not work, guys. Instead, your object needs to be inside the focal length. Okay, and now what we're going to do, we're going to draw our light rays. Okay, the first one is in parallel to the principal axis and out through the focal point, like so. Okay, that's our first line drawn. Our second line, or our second light ray, in parallel to the, in towards the pole, creates an angle I, and the reflected light ray will come out with the same angle. Now, what we can see from these two light rays is that they are getting further away, or they are diverging in front of the mirror. So as a result, what we need to do is we need to trace these light rays backwards, and when we do that, we see that eventually they will meet at this point here. Okay, so it's at that point where the two light rays converge, that is where our image will form. Okay, so I'm going to call that our image. Okay, very important, guys. If it's a upright image in a concave mirror, it's going to form behind the mirror, which means that it is a virtual image. Okay, so I hope that makes sense to everyone so far. Let's just have a look back through. That is our 2018 question complete. So far, so good. Okay, now let's move on to our next question, 2017 question 12, part C. So, in the 17th century, we had a Dutch artist, Rembrandt, who used a concave mirror to help him sketch self-portraits by projecting an inverted, that's key thing to note, guys, it's inverted, so it's upside down, onto a copper sheet, and it's been projected onto a copper sheet, so we know that it's a real image because it's been projected onto a screen. Okay, draw a ray diagram to illustrate how Rembrandt used a concave mirror in this way. So this, guys, is slightly different to the previous light ray diagram that we're after drawing, in that it's a real image forming this time. So again, we're going to draw our concave mirror, dash line at the back indicating that that's the back of our mirror, and we're going to put our focal length there. Now, I'm simply just going to put our object. For a real image to form, the object must be outside the focal length. We might make it a little bit smaller. And that's our object. Okay. Next up, we've got our light ray rules. In parallel to the principal axis, out through the focal point. Okay. Our next one that we can draw, apologies, is in through the focal point, out parallel to the principal axis. Go again with that. Struggling with this. Okay, so here we go. That's us done with our two light ray diagrams, and we can see that our light rays are intersecting all the way back here. So this is where our image will form. We can see in this case our image is magnified, it's bigger than the object, and as well as that, it's been inverted, it's upside down. So that's us finished with our first question. Now let's move on. He used a concave mirror of focal length 60 centimeters. So we know the focal length is 60 centimeters, so that the image on the copper sheet was only half the size of the object. So we know the image is, or the magnification is half that of the object. So what we've been asked to calculate, the distance from the sheet to the mirror, okay, so where our image is forming, and the distance from the object to the mirror. Okay, so let's write out the information that we know. The focal length is 60 centimeters and the magnification is a half. Okay, so let's go with this. Firstly, our magnification formula is V over U. Subbing in a half for our magnification, V over U. And at this point we can cross multiply above the line by below the line, and you get that 1 times u is equals to 2 times v, 2v. So that's our next piece of information that we know. U is equals to 2v. Our object is twice the size of our image, where v is our image. Okay, next formula that we're going to write out. 1 over u plus 1 over v is equals to 1 over f. And we're going to start subbing in all the information that we've got here. We know that u is equals to 2 times v plus 1 over v. We don't know what v is. And we know that our focal length is 60 centimeters. So, we're in a good place so far. Lowest common multiple between 2v and v is 2v. 2v will go into 2v once, plus v will go into 2v twice. And that equals to 1 over 60 centimeters. So far so good. We've now got 3 over 2v is equals to 1 over 60. And again, at this point, what we can do is cross multiply. Above the line by below the line by above the line on the far side. Okay. 2v times 1 stays as 2v. 3 times 60 becomes 180. Divide both sides by 2. And your 2 cancels with 2. We're left with v is equals to 180 divided by 2 gives us v is equals to 90 centimeters. So that's pretty good. We now know that the image will form at 90 centimeters. The next thing we can do, or the next thing we've been asked to do, is find where the object is. Okay, well, the object is 2 times the image from earlier on. Okay, we got this from our magnification formula earlier on. So u is equals to 2 times v, which we now know is 90 centimeters. So u, our object, is 180 centimeters from the mirror. Okay, so there we go. That's our second part of the question that we've been asked. So we've done everything so far. Up next, a concave mirror can also be used to produce an upright image. Explain why this is not of use to Rembrandt. So what we're going to do is I'm just going to take you back to our previous question and have a look at the light ray diagram that we sketched. Okay, so down here at the bottom we can see here we've got our upright image. Okay, however, this is a virtual image. It's formed behind the mirror. You cannot put a screen behind the mirror, so therefore it can't be projected onto a screen. So that is our answer. The answer to this question is, explain why this image is not of use to Rembrandt. An upright image will be virtual, therefore cannot be projected onto a screen. Okay, so I hope that helps you out, guys. That is our second question, 2017, question 12, part C, complete. And we're still recording. Super. Okay, so we're going to have a look now at our next question, 2014, question 12b. Okay. So, first up, what is reflection? Small little definition for 3 marks, an easy 3 marks. Everyone should be aware of their definitions. Reflection is the bouncing of light of the surface of an object. Okay, that's our first 3 marks on reflection. Okay, up next, we've been asked to draw our light ray diagram to show the formation of an image in a convex mirror. Okay, so this is the first time we've been asked a question on a convex mirror. Again, first things first, guys. Well, we're not going to go in green. We're going to draw our principal axes. And we're going to remember our convex mirror, guys, bulges out at the center rather than caving in at the center like a concave mirror. Our dashed line represents the back of our concave mirror, and again we need to note that our center of curvature C is the center of the curve is behind the mirror this time, and our focal length, I'm just guesstimating here, guys, you need to use a ruler to get this as accurate as you can. Your focal length is halfway between the center of curvature and the pole of our mirror. Up next, we're going to place our object in front of our mirror. That's the object, again, just a simple arrow. And we're going to start drawing our light rays now. So, first light ray in parallel to the principal axis and out, has been reflected out of the surface then as if it's coming from the focal point. Okay, so if I just trace that backwards, again, you guys are going to use a ruler when doing this, okay, to make it more accurate. That's our first undo that. That's our first light ray. Our second light ray, guys, I'm just going to draw towards the center of curvature. Remember, if a light ray is coming in from the center of curvature, if it's heading in towards the center of curvature, it just reflects back along its own path. Okay, so if it comes in if it comes in from the center of curvature, it'll just be reflected back out. Okay, and we can see these two light rays in front of the mirror, if we call them light ray 1 and light ray 2, they're never actually going to meet. They're diverging. They're getting further away from each other in front of the mirror, so we need to go behind the mirror. And we can see now behind the mirror, our light rays appear to intersect. Okay, and where that apparent intersection is, that is where the image is going to form. So we can see here, in this case, our image is upright, it's behind the mirror, so it's virtual, and it's diminished. And that's us done with our light ray diagrams. Very, very important to be able to draw all our light ray diagrams, guys. Excuse me. Okay, so next question. Person looks at a shiny spherical decoration when her face is 30 centimeters from the surface. Okay, so that is the object in this case. It's her face 30 centimeters from the surface of the decoration, and the diameter of the decoration is 20 centimeters. We want to find the position of the image. So that's what we've been asked to find. Okay, so let's imagine there is our decoration, and we've been told that the diameter of that is 10 centimeters. Therefore the radius, 10 centimeters, 20 centimeters. Therefore the radius is going to be 10 centimeters. Now we should recall, if we just look back up at the diagram that we did previously, the center of curvature equates to the radius. Okay, so now we know that the distance from the center of curvature to the pole is 10 centimeters. Therefore, the focal length is 5 centimeters. Okay, so there's a little bit of deduction from that. So our focal length would be there on our diagram. So information we know, focal length is 5 centimeters, and we were told that her face, in this case the object, is 30 centimeters. Find V where the image will form. Let's write out our formula. 1 over U minus 1 over V is equals to minus 1 over F. Your question could be, why have we got a minus in front of our V and a minus in front of our focal length? Okay, and the reason being, if we have a look at our diagram again back up here, the focal length and the image are behind the mirror, behind the reflecting surface, so therefore we're putting a minus into both places in our formula. Okay, so let's start filling in our information. 1 over 30 minus 1 over V is equals to minus 1 over 5. Next thing we need to do, bring our 1 over 30 across the equal sign, so that we've what we don't know on the left hand side, in this case V, and everything we do know, all our known values, on the right hand side. We take something across the equal sign, we must change sign, and now we can see we've a plus, or our plus becomes a minus, and we've 3 minuses. So what I'm just going to do to make this simpler is I'm going to change all 3 of those signs. If I change one sign, I must change all the signs. Simply do that by multiplying by minus 1, and all those negatives become positive. 1 over V is equals to, grab your calculator, 1 over 5 plus 1 over 30 becomes 7 over 30. Last step, flip your fraction around. If you flip it on one side, you must flip it on the other side, and you get that V is equals to 30 over 7. And V becomes 30 divided by 7, 4.29 centimeters is where our image is going to form. Super. So we found where our image is going to form. For the final 4 marks, concave mirrors rather than convex mirrors are used by dentists to examine teeth. Explain why. Again, I'm going to go back to our previous diagram. If we have a look here, our first light ray diagram that we drew, we can see here's a concave mirror, and we can see we've got our object. In this case, if we're talking about our dentist, our teeth, inside our focal length. If the object or your teeth are inside the focal length of the concave mirror, well, the image that forms appears magnified. So that's why dentists or beauticians mirrors or shaving mirrors are used. Okay, so concave mirror is used because it can produce a magnified image. Super. And that is our 2014 12B question complete. Okay, 28 marks in the bag, half a question complete in good time as well. Okay, so again, I hope that's clear to everybody. The final question we're going to have a look at today is a question 2005, question 5 part D. So it's a 7 mark question, so shouldn't take us too long. It's going to be a simple enough question. We're told that the object is placed 30 centimeters in front of a concave mirror of focal length 10 centimeters. How far from the mirror is the image formed? Okay, always guys, write out your formula to pick up marks. Even if it's a 7 mark question, you're going to get 3 marks just for writing out this formula, I imagine, which is not to be snubbed. Now let's start subbing in. Take out U and we're going to put in 30. V is what we don't know, and we're taking out F and we're putting in 10 centimeters. Again, we're going to take all our known values to the right hand side of our equal sign, leave our unknowns on the left hand side. When you take something across an equal sign, it changes sign. Grab your calculator. 1 over 10 subtract 1 over 30 will give us 1 over 15. Last step, we're looking for V, not 1 over V. So flip both fractions around and you get V over 1 is equals to 15 over 1. Anything divided by 1 stays the same. So V is 15 centimeters. And that is our 7-mark question complete. I hope this video has been of benefit to you guys. So here we've had a look at the solutions to all our reflection and spherical mirror questions. So I hope you found that beneficial, and thank you very much for watching. All the best.